let's go back to the beginning of chapter 2, where we had a free particle Schrodinger equation. We had the time-dependent Schrodinger equation for a free particle. And recall that we had a particular solution to this equation was a free particle of plane wave. And this is a pure mode solution. And we have the wave number and the frequency. And they have to, if you substitute this into this equation, for it to be a solution, there has to be a relationship between omega and k, this dispersion relation for the free particle Schrodinger equation. So I might write that this omega here is a function of k. This is that relationship. So for k positive, this wave travels to the right. And for k negative, it's traveling to the left. And the homework that you were doing today, and when I talked about the lecture on Wednesday, we calculated the current density for this. And we found that the current density, let's see, the probability density is just uniform, a squared. The current density was h bar k over m, 5a squared. And remembering that the Broglie relation and the velocity times a squared, so the current density divided by the probability is like a velocity. Now this is an average velocity in general for a sub-ensemble. So we look at some location x, and in that location, so we have some location here, we have a bunch of particles. What I mean is different ensembles, different members of the ensemble will have a particle in this interval. Some will not, most will not, but some will have a particle in this interval. And that average velocity then is the average of those in that little interval. So this is a function of, possibly a function of x and time. But in this particular example, it's constant. It doesn't change with x or t. Okay, and you've also studied superpositions. So we can take two different values of k. So this is a superposition of two plane waves, and you've looked at this some in your homework. And so we're coming to understand now that the magnitude squared of the coefficient is associated with the strength of that plane wave, the probability. And there's a probability associated with being the plane wave. But the superposition has things that are beyond the individual probabilities. The probability is not the sum of the two individual probabilities. Probability is the wave function is a superposition. So the probability associated with the superposition, you have to take all of this, square it, so you get cross terms. The interference terms then depend a lot on the magnitude and the phases of these complex numbers. A1 and A2 are complex numbers. The details of this superposition depend on the phase relation as well as the magnitudes of A1 and A2. It's the arguments of those complex numbers. Okay, and now we can add up a third. We can have any number of plane waves, add them together, get a superposition. It's another solution to the time-dependent Schrodinger equation for a free particle. And so we continue this process. We could write it this way, as a sum over an infinite number of plane waves. The integral is a sum. So this is another superposition that involves possibly an infinite number of plane waves. So phi of k here is the strength of each component in the superposition. And phi of k squared will be the probability of just that piece by itself, if there were only that piece, but there's a superposition. So this is a complex function. So the magnitude and the phase are important in the superposition. And so recall back at the beginning of chapter 2, we had an exercise to demonstrate that this very general solution, very general expression, was indeed a solution to the free particle time-dependent Schrodinger, represented as superposition plane waves, so pure modes. And that's something I've been repeating without demonstrating it to you in general. The general solution, even not for the free particle, but if we add in the potential energy, if we find the pure modes, then the general solution to the problem is given as a superposition of pure modes. So this is a general characteristic. For the free particle, the pure modes are these plane waves. And so this is a superposition of those pure modes. Notice K goes from minus infinity to plus infinity. Again, here, when K is less than 0, those are left traveling waves. K is greater than 0, those are right traveling waves. So this has a sum of left and right traveling waves, all with different wave numbers, which is like spatial frequency. Remember, the wave number is related to the de Broglie wavelength. So what we're doing is constructing a wave function out of different wavelengths. This is analogous to having sound, which is a superposition of different frequencies. The sounds that you hear all around you during the day are not pure modes. They're not usually single frequencies. It's got all kinds of frequencies mixed in. And so this is similar sort of expression. Okay, so this is all review. Everybody remember this? Any questions about this? Okay, so now we're going to focus on this problem here, on this expression. So if I had phi of k and I knew how to do this integral, then I could get the wave function. Right? So you'd have to know how to do the integral. But so if I have some function, suppose it's a Gaussian, for example, it could be a Gaussian k. Then I have to know how to do this integral. And remember, this is k goes like k squared here. So it's not a trivial integral in general to do this, but that's the idea. So the question is, if we know the wave function, can we find phi of k? Can we go back? So in other words, how do we go? This takes us from phi to the wave function, and we go the other way. What I mean is from psi of x to phi of k. Go backwards. And that's the subject of the next lesson, this inverse process. Okay, so it involves a very interesting thing called, back to the Dirac delta function. Another way to express the Dirac delta function is different, but related to what we did before, is this integral. Very interesting integral. So it's an integral. If we take out the time dependence here, we just look at the k dependence, just the x by itself. Then this integral is the Dirac delta function. I'm going to demonstrate that in your homework, but I'm going to going to give you an idea about why this is true. Now remember, this is 0 everywhere except when x is equal to 0. So let's look at the case where x is equal to 0, and we should get a divergent interval. So we set x equals to 0 here. We get this interval. The area under constant function. That's clearly divergent. And that corresponds to the peak of the delta function. Well, what if x is not equal to 0? Then we should always get 0 from this expression. Okay, so let's suppose that x is not equal to 0. Let's look at it this way. Let's write this in terms of the Euler relation. Like this. And we're going to find the area under this function. Integrating with respect to k. So let's plot this. Let's plot the real part and then plot the imaginary part. So the real part looks like this as a function of k, where x not equal to 0. Where this distance here is 2 pi over x. So what's the area under that curve? That just as much positive as negative. Now there's a little bit of a problem here because it's a little bit ill-defined because it depends on where you put these limits. I put the limits here right at the right place here where the area cancels out. It's a little tricky because what if I chose the limits here so that it was a little bit more positive than negative? We're extending this integral to infinity. So you have to be a little careful about doing this integral. But your homework, you're going to be more careful about how to do that. But the area under this curve, if you let me just draw that portion, is 0. So the argument is that we have the oscillating function and that the average is going to be 0. Okay, then the same argument holds for the sine part. It's just as much positive as negative under the curve. And so the argument is, and you have to be a little careful about this, right? I'm being kind of quick here. You're going to be more careful. This is equal to 0. That's not. So that's like this delta function. Infinite of x is equal to 0, but it's 0 for any x not 0. And you have to, I put in a factor of 2 pi here. It's not obvious why there should be a 2 pi. In your homework, you'll find why that 2 pi. So this is a really interesting relationship. And we're going to make use of this. So, writing it like this, we also can write it the other way around, just swapping symbols. Writing it as an integral over x, again, we get this delta function of k. We're just swapping symbols, so that can't matter. Okay, and also let's suppose we have e to the I k minus k prime. Difference in k is here, integrate over x. Well, it's not exactly the same, no, but it's very similar. It's almost a trivial step.
Oh, it'd be 0 at k prime, right?
0 when k equals k prime. Right. So in terms of the delta function, that would be right. K prime. Very good. By the same argument, whatever that thing is, multiplying the x there has to be 0 or to get anything not 0. Delta K minus K prime. Okay, so let's go back to this. I'm going to do this first. Oops. I'm going to do this first at time 0. Go back to this expression. Just because it makes it a little bit simpler. But the whole thing follows through even at any time. Okay. See how they go now to do it, to go from here to here? This. So let's multiply both sides by e to the minus I k prime x. Okay, and that doesn't depend on k, so I'm just going to bring it as a right. This doesn't depend on k. So I'm going to, this is a sum multiplied by a constant. I can distribute that constant through the sum. Okay with that? And then I'm going to integrate over x, both sides. Right. In this equation, this is a function on the left side and a function on the right side. But this function is the result of doing an interval. It's a function of x. So don't get confused here. Remember, k has no particular value. K is a dummy index. This represents the sum of individual k values, but it's infinitely potential range. Okay, so now I integrate. I multiply by this function of x, and then I integrate over x. So this side is a function of k prime. And the right-hand side is some function of k prime. You have a double integral. That's what you have to do. Okay, so this is then finding the area under a two-dimensional function. So we have a two-dimensional function. We want to know the area under that two-dimensional function. So we have an integral over k and an integral over x. I can't draw. There's some function here which is a function of x and k, and this two-dimensional integral is the area of the volume, actually the volume under this curve, under the surface. So it doesn't matter the order of integration. Volume under that surface doesn't matter the order in which I do the integral. So I'm going to swap the order of integration. Okay. So we have, I'm going to do the integral over x first. So I have u minus k minus k prime x dx. But phi of k doesn't depend on x. So I can pull it out of that integral. I can do this integral first. Well, bingo. This is 2 pi times delta function k minus k. This was all equal to, well, okay, yeah, this integral here is then equal to this. Okay, so then we have 2 pi times phi of k times delta k minus k prime. Okay. All right. Remember the delta function, we defined it in terms of an integral like this. Some function times a delta function. If this peaks non-zero, oh, yeah, k prime, right? K is a dummy index here. K prime is some particular value. So this is 0 except for k is equal to k prime. So it fills out the value of phi at k prime. So this is equal to phi at k prime. And remember, all of this was equal to this function of k prime. So we have phi of k prime, 1 over 2 pi times the integral phi of x at 0 times e to the minus I k prime x dx. We accomplished what we needed, which was to go from the wave function in x to this, the amplitude for k. And I can erase the k prime here. I can just make it a k, right? Don't get confused now, because previously we used k as a dummy index, but I could write this as a function of k. It's a function of some argument. So I can erase the k here because I'm not using, in this expression, I'm not using k for anything else. Like I could call it k prime or k, whatever I like. Okay, so we went from here to here. And look, it's like the same integral. It's the same kind of integral. Here we're taking phi of k, multiplying it by e to the ikx, we integrate, and we get psi. You take psi, multiply by e to the minus ikx, integrate over x, and we get 5k. Beautifully symmetric. So, in fact, there's a kind of relationship between k and x. There's a kind of reciprocal relationship between them. Remember, k is like a spatial frequency. So it's the same sort of relationship holds in sound. There's the time. There's the sound that progresses over time. There's a frequency content of that sound. So this is pulling out the intensity at some given spatial frequency. It's like doing a frequency analysis of the sound that you're hearing. Very similar to that. So this is a spectral analysis. Given some instead of depending on t, it depends on x. So you can imagine that there's a similar equation I could write for t. Given a sound that takes place over some time, find the intensity of the frequency of each contribution to the sound. So this is a spectral content. Pulling out the spatial frequencies that contribute when superimposed to give that wave function. Beautifully simple. It's amazing symmetry between these two intervals.
Say the spectral. This is in the book.
Yes. Well, no, actually, I mean, I give you a handout you're going to read that fleshes it out a little bit more. It's in the book. You're going to read about it in the book. But I'm going to step you through it a little bit because you're not familiar with this math, and the book doesn't go into the details as much. So it's a lot of it is in the book, but not this kind of detail.
Trying to understand since say spectral content.
Yeah.
What do you mean by that again?
Okay, so you have that makes the analogy to sound. You're a sound that takes place over some duration of time, and then you can do a spectral analysis of that sound. Meaning, tell me how much different frequencies contributed to making that sound. Right, the sound that you hear is a mixture of a lot of different frequencies. And that's what you're hearing. You hear it all at once. I mean, you hear it over the duration. But this will allow you to break up the sound at time to a frequency spectrum. What are the frequencies that contribute to that sound? This is analogous now. Instead of time, we have x, and we have a spatial frequency. Wave.
So it's like giving you the superposition. You're able to figure out what are all the particulars that's composed of superposition.
Exactly.
That's amazing.
Yeah, it's cool. It's really neat.
psi of x, why is phi of k? How is phi of k giving you that? That's what I'm actually using. Like, why is phi of k breaking that up? Why is it giving a breakup of that?
Well, this is what's doing the breaking up. And the reason comes from here. You can see this right here. Right? We multiply by e to the minus ikx. And then this integral is not zero only where k prime, I'm sorry, e to the minus ik prime x. This integral is non-zero only where k prime, I'm sorry, k matches k prime. So it's like filtering out the part that you want, which is phi of k.
So it gives you one particular, it only gives you one particular.
No, it's a function of k. But you have to do it, you know, you get a function of k here by doing this integral for different values of k, but you know how to do variables, so you do it as a function of k. So this integral is a function of k. Right? X here is a dummy index. This integral gives you a different value for each value of k. So this integral is a function of k.
Hit it on the spot, hit it on the side.
Yeah, right.
And you just plug in as many k's you can to solve.
Well, that's you only need to do it once, right? Because you know how to do integrals. It's a function of k. Depends on k. Let's see how this works. Take some examples. Okay, so let's see. The other step was I did this at t equals to 0. Okay, so the other step here would be what happens when t is not 0. But the key point is that this allows you, if you have the initial wave function, you get phi of k, but now you can superimpose that with the expression that we had here. You find what the wave function is always time. Right? Phi of k here is determined at t equals to 0, and then you can find the wave function at a later time. You're solving Schrodinger's equation for a given initial wave function. So this is a way of solving Schrodinger's time-dependent wave equation for a free particle. In other words, this comes from the initial wave function right here. And from that, you can get the wave function at a later time. So it's a way of getting the solution to the Schrodinger equation. It's one way. There are other ways, but it's a way of getting solving Schrodinger. Schrodinger equation tells you how the wave function evolves in time. That's this time derivative here. And so generally we view this as a way of taking an initial wave function, some initial wave function, and finding out its value at a later time. So how do you set it up? Well, we haven't discussed that yet. How do you set it up? But that's what the Schrodinger equation, the content of the Schrodinger equation is. Given some initial ensemble wave function, how do you find what it does later? And this is one way of doing it. So we did it through this. Remember, this integral is different than this one, previous one, because we did it as equals to 0. Now we have to have that frequency here. And so there's a k squared here in this integral. So this is going to be different than the one at time equals to 0. And it's the dispersion relation that tells you that how the wave function is going to change in time. That's another way of expressing through that dispersion relation, which comes from the free particle Schrodinger equation. That omega of k we found from so all of this works only for a free particle. Right? I mean, there's something analogous to this for other situations, but what we're doing right here is just free particle. Okay, so this mathematical symmetry logical relationship between these two equations. So mathematically, this is expressed as a transform. So a transform takes a function to a function. So I have some function in general, and I want to find another function which is defined by this interval. So g of k is the interval of e to the minus I kx f of x. And to make this symmetrical, more symmetrical, we put in a factor. Usually put in a factor of 1 over root 2 here. And then the inverse goes from g of k back to f of x. It's amazing how symmetrical this is, because it looks like the same integral. The only difference being we have a negative sign here, this positive sign. Yes.
Yes. That's like a complex conjugate of it. It's like,
Yeah.
it's like the root.
That's right. And so, in fact, you can show that this works for any, if these integrals are doable, you can show that this is self-consistent. So I could take g of k from here, plug it into here, and get back to f of x. Let's try that. I'm going to put here, the g of k, I'm going to put all this here. So we should get f of x. In other words, we go from f to g, and then we should go, if we come back using this inverse transform, we should come back to f. Okay, let's see what happens. So now for g of k, we put all this. I've got to put here, I've got to be careful. I've got too many x's floating around here, so I need to write this as a prime here. But if I substitute for g of k, this integral involving x, I've used x in 2 different places. They're not the same thing. So I'm putting a prime on this right now for this demonstration here. That's a prime. Oh, this is a prime. Okay, and this is an integral over x. Okay. Let's see. No, I've done something wrong. X prime here.
Right next to dx dk also need a prime or no?
Let's see here. F of x prime, dx prime. Yeah.
So wouldn't that just be normal?
I think I've done something wrong here. Hang on.
Yeah, why is there a p for your prime?
Because this, I'm using x twice. Here it's a dummy index, but here it's not. I can't use the same x. Because then I can't substitute this in with using that simple x, which means something different from this x. So I give this one a different name. Make sure I don't get confused. It means 2 different things. So I changed the name of this. Okay, so then we have g of k. G of k is this. Okay. Now again, with this, the order of integration here doesn't matter. So again, a 2-dimensional integral, the order doesn't matter. I'm going to bring out the 1 over root 2 pi. We have 2 pi here now. This. can pull the f of x out because this piece doesn't depend on x. I mean, it's not integrating over x. This is an integral over k. So I can pull this f of x out, the constant over the sides. Well, bingo, what is this?
What's the
Delta function here, right? So there's 2 pi times the delta function of x prime minus x. Okay, so I've done that integral. That's in the square bracket here. So we have f of x prime is equal to, and we have 2 pi here and the 2 pi there cancel. So what's that?
f of x prime.
Yeah, it's f of x prime. So in other words, I've just proven that the transform and its inverse are faithful. That is, if you do the transform and you do the inverse transform, you should come back to what you started. That's assuming all of these integrals converge, right? Both of these are converge. That is an assumption in all of this, that these integrals are defined. And we've got this tricky thing with the delta function that keeps throwing in. So there is some concern about this. You have to be more rigorous, not being really careful here, but it all does work out. The rigor is there. It's just I'm not showing. Okay. Well, let's take a for instance. Let's suppose I have a function at time 0, which is back to that plane wave again. Try this and see what we get for 5k. Now, we do the inverse. Well, let's see first. Hang on. We're going to do that here, but let me show you something first. I'm going to do it first. I'm going to turn this back on. So on Canvas, you should download from Canvas. It's a one-sheet table of Fourier transforms. So it's like an integral table, so you don't have to do these integrals. It's all carefully done for you here. So you can just look up and use the table, just like you do with integral tables. You should be able to do integrals, but once you know how to do them in principle, then frequently you just look them up. So here's that table. This is what's on Canvas. So the column on the left is f of x, and the column on the right is g of k. And so you can see that when we do this, and if, for those on Zoom, you'll have to download this because you probably can't see the screen here. So the transform f of x gives g of k, which is root 2 pi times delta of k. And so also it would go back. So g of k ought to go back to this, or another way of seeing it is because of the symmetrical relationship. This delta of x transform just gives you 1. So for every entry here, there's another one farther down which goes in the opposite direction. It's very symmetrical. So there's repeated, what looks almost like a repeated entry. Okay, so there's cosine of kx, sine of kx, e to the ikx. That's the one I was about to do for you. You should get a delta function there. Here's a Gaussian. You're going to use a Gaussian. The Fourier transform of a Gaussian is a Gaussian. Very simple. Really cool. So if I want a Gaussian sound, then you have to have a Gaussian frequency spectrum. You get a Gaussian in time. Pretty cool. Okay, so let's see how this works then. I want to demonstrate this to you. But you should make use of that table. The integrals are pretty simple, actually. Some of you may be able to do the integrals without looking them up. but I made them available to you because I don't really want you to spend a lot of time doing that. Just look them up in the paper. Okay, so. All right, let's slowly start with this. I'm going to use a different symbol here for the K because we're going to have phi of K, which is a different meaning again. So let's call it a capital K. It's a single plane-wave. And we can put a constant from. Okay, so phi of K is 1 over 2 pi. That's the integral of psi of x0 times e to the minus I k x dx. That's the inverse. So there's this funny factor of 2 pi's floating around. It's generally in the mathematical definitions, the 2 pi factor is broken up into 2 square roots of 2 pi and set it up so it's very symmetrical. It's the same 1 over root 2 pi in the forward transform and in the back transform. Okay, so just be aware of that. So the way I did it first here, I didn't write it that way. I just wrote it like this. Okay, so this is, I can bring the A out. A is a constant, doesn't depend on X. What's that?
Oh, that's just like in the direct line.
That's delta. Remember, delta of x and delta of minus x is an even function, so I can just change the sign here, make it prettier. Okay, so really this is pretty obvious, right? This is the function, the spectral frequency. Well, there's only one wave, there's only one wave number, only one spectral frequency, which is big K. Because that's all there is. So if we go backwards, then we should be able to take this and go backwards. Remember we said psi of x of 0 should be the integral of the superposition, right? Phi of k e to the I kx dk. Let's put phi of k in there. Again, the factor of a comes out from, we have delta k minus big K. Integrating over little k, and with a, see here.
Flip flop your K right there.
What's that?
You flip flop.
Oh, this is right. This is right. Sorry. Yeah, I can flip it here. This because this is an even function. Oh, right. Delta of x and delta of minus x is the same. Even function. So what's that integral? It's the area under delta function. Hold on. Here we go. I need to have this. Here we go. That's what's in there. Okay, so remember the definition of the delta function multiplied by a function integrated gives me that function evaluated for the delta function, the argument of the delta function is 0. So k is the integration variable here. So this is 0 everywhere except k is equal to big K. And so this gives e to the I big K start. Got a couple minutes yet. All right. Well, let's try something. Let's try this. To K1 and K2, two different values of K. It's a superposition of two different plane waves. Maybe K1 and K2 could be opposite, like have a left and right traveling. Okay, what do you think phi of K is going to look like? Everything is linear. of the sum is the sum of the transforms. All of this is linear stuff. So what is the transform of this? We just did it. What is the transform of this? Well, so this spectrum has two peaks in it. One at K1, big K1, and the other at big K2. And those are the two modes that contribute. And notice that the A comes through here. Remember, A1 and A2 are usually complex numbers. So there's magnitude and a phase relation. The phase relation is important. The Fourier transform preserves the phase, doesn't get rid of it. And it's important in the inverse that those phases are still there. Because to go back from here to here, you can't lose the phases. Phases, that's important. Complex numbers here are complex. Don't forget that. Sometimes I'll tell you just assume they're real. Yes.
Well, I'm confused that when the magnitude of the guy wants to give you the magnitude of phi of k, when that delta, direct delta equals 0, it shoots to infinity, right?
When the argument of the delta function is 0. So this thing has two peaks in it. Here's 5k. Function k. Here's two delta functions. Boom, boom. And each one has a strength A1 and each K2 like this.
But not like the actual like height. It's like infinity times that, right?
Well, that's right. That's the funny thing about the Dirac delta function. Remember, it's a very singular function. 0 everywhere except it's infinite at one point. So it seems kind of tricky. You have to be careful about this. And I'm not showing you all the rigor associated with defining the delta function, but it all works. If you just remember things like this, delta x minus y f of x dx equal to f of y, right? Just remember that. That's really a good way to define the delta function. That this interval is equal to f of y for any f. And so the delta function is a very singular function. So you can make these things more rigorous by treating the delta function as having some kind of like a Gaussian with some width, and then take the limit as the width goes to 0, for example. That might make it a little bit more clear about delta function, because these peaks in that case would be like this, and then you take the limit. Remember, this height is like 1 over the width, and this width goes like sigma, so the area is 1. Then you take the limit as sigma goes to 0. Everything works. I haven't dragged you through all of that, but to just make it work. Okay, any other questions? So you've got a worksheet that'll step you through this and come back to what I did today in class. Watch the Zoom again. All right, so we'll see you on Monday.